Central to the alternative interpretation of physics of this series is that the universe may have an infinite scalar dimension, which would mean that there are infinitely larger regions of space beyond the observable universe, and that there are infinitely smaller regions of space below the Planck length. This video will be devoted to exploring why it may be possible for the scale of the universe to be infinite in scale, and will argue against some of the common criticisms of such an idea. But unlike with locality, which is opposed by the majority of scientists, there's actually some support for the idea that the scale of the universe could be infinite, although this is far from a consensus opinion. Well, there isn't any real scientific consensus at the moment, because there isn't enough information available to make a definitive statement about the size and shape of all of reality. This lack of hard data has allowed for a wide variety of opinions on the topic. But, despite this, it's commonly believed that there are still limits to scale. Even when physicists do entertain the idea that the universe could be infinite in size, they will usually also believe that there are limits to how large and small things can be. That the formation of matter and energy only occurs within a limited range of scale within an infinitely larger universe. In this video, I will try to make an argument in favor of the universe not only having an infinite scale, but also that it may be possible for matter and energy to exist within infinitely many larger and smaller regions of space. This will form the basis for how this local and real model could work. So what is meant by scale? To start, it involves focusing on differently sized regions of space. At the quantum scale, which encompasses the smallest sizes we can observe, there are atoms and particles. At our scale are a wide variety of plant and animal life. And at the cosmic scale are the stars and galaxies and the largest structures we are capable of observing. But scale isn't just about size. It's how all of these things can exist within the same region of space. Let's consider this cat. If we were to scale down, or zoom in, on just this cat, then we could see that they are made up of a multitude of cells. And these cells are made of different organelles that are made from molecules. And these molecules are made of atoms that are themselves made of electrons, protons, and neutrons. And protons and neutrons are made of quarks. And if we were to zoom out, or scale up, beyond this cat, we would see that it exists at some location, on some landmass, on the planet Earth. And that this is just one planet within a solar system. And this solar system is just one of billions that exist in the Milky Way galaxy, which itself is just one galaxy among thousands in the Laniakea supercluster, which is just one supercluster of galaxies among many in our observable universe. All of these things exist in the same location in space-time, just at different scales, all centered on this one cat. Basically, scale is about how things exist at different sizes within the same region of space, and how smaller scale objects interact with each other or accumulate into larger scale structures. If scale had a unit of measurement, it would have to be some cubic volume of space-time, or at least it would need to be some three-dimensional region of space. This volume wouldn't just describe the scale under consideration, it would provide a frame of reference from which comparisons could be made between other objects of radically different sizes. But is there any reason to expect the scale of the universe to actually be infinite? Well, we will only ever be able to view and make measurements of what is within the observable universe, a limit defined by the speed of light and the expansion of space-time. Since our knowledge of reality will always be limited, we may never fully know or understand its true size and shape. However, what evidence does exist seems to point towards the universe being flat and infinite in shape. What this means is that if you had two parallel lines that traveled together in the same direction forever, then they would always remain parallel to each other as they traveled through space. One interpretation of this would be that the universe really is flat and infinite in size. It's not the only possibility, but if this were true, it would directly imply that there's also an infinitely larger scale, as it would always be possible to consider a larger volume of space-time than whatever region is currently being considered. For example, we can start by looking at our observable universe, then expanding to consider a region of space that is hundreds of trillions of times this diameter. The observable universe would be nothing but an insignificant speck within this larger region, and whatever exists would be made up of the accumulation and interactions of our observable universe and all the other matter and energy that exists around it for some septillion light-years across. But if the universe is infinitely large, then there are no limits to scale. So we could then consider a region of space that is hundreds of trillions of times larger than this larger one. and we could keep on repeating this out forever. Even if we reach a point in scale where nothing exists, it would still be possible to look at infinitely larger volumes of spacetime above this region. So if the size of the universe is infinite, then it must mean that infinitely many larger scales exist. Going infinitely smaller in scale is a bit harder to reason out directly. It involves being able to infinitely subdivide a region of spacetime under consideration. However, we shouldn't have a unique position or perspective within the universe. So if infinitely many larger scales exist above us that we can zoom out to view, then we should be able to zoom in on infinitely smaller scales. Otherwise, it would mean that we have a unique position in the universe. That in a universe with an infinite expanse, that we are somehow on the ground floor of reality. Even so, it appears that most physicists believe that nothing can be smaller than the Planck length. But this is not a proven fact of science, just one interpretation of the math. The Planck length is often cited as a hard physical limit of the universe. According to many physicists, it is the smallest possible size, after which space can no longer be subdivided into smaller regions. However, not even all physicists think this is a true physical limit to the universe, as there is no direct evidence beyond assumption and inference. The Planck length came from the work of Max Planck, who wanted to create units of measurement that were based on nothing more than the fundamental constants of the universe. By combining these in a particular way, it's possible to arrive at several units of measurement, including the Planck length, which is an incredibly small unit of distance. So it's a unit of measurement based on the values of the constants of nature. It's often believed to be a hard limit to the universe because our understanding of physics breaks down at this scale. The equations for the laws of physics start to go to infinity when pushed beyond this distance. The standard model just breaks down at this limit. Additionally, it has been worked out that the Planck length is the theoretical limit to which we could ever possibly measure in the universe. If a researcher tried using photons to probe a region of spacetime smaller than the Planck length, they would end up putting so much energy into that one location that it would start to create distortions larger than the Planck length itself. This would create an uncertainty in the measurement larger than the area being looked at. That uncertainty only grows as the area being measured decreases in size. So the Planck length is also the theoretical smallest size that we could ever possibly measure. For reasons like this, many physicists have come to believe that this is a hard limit to the size of the universe, that nothing can be smaller than the Planck length. But this is just one possible interpretation of these results, because there's nothing in the data that actually says that this is the smallest size of the universe. It's just an inference. It's at least equally valid to interpret the data as just a part of how the field of physics is incomplete, because this is still consistent with the universe having an infinite scalar dimension. We exist within a particular scale that is of a particular size, and are made from matter that is also of a particular size. This sets a physical limit on what we can observe and do in the universe. What we see happen at the Planck scale could easily be the result of observational limitations and biases. At our position in the scalar dimension, the smallest quantum phenomenon we can easily measure, control, and manipulate are photons. This automatically sets a limit to what is possible for us, because photons have a physical presence in our universe. They have definitive properties that we can study and measure. Since there are limits to what we can observe and measure based on the properties of photons, it puts us in an observational bubble. But not necessarily because the universe ends, but because of the limitations imposed by the tools we have at our disposal to examine the universe. Additionally, the researcher, the photon, the measuring device, and the thing being studied are all part of the same universe. When researchers take measurements of reality, they are doing so as a part of the universe, using another part of the universe to measure an aspect of the universe, all from the perspective of us at our scale. So we should expect limits in our ability to observe the universe. The fact that we can't use photons to probe a region smaller than the Planck length doesn't necessarily mean that it's a sign that there's a bottom floor to the universe. Because it could just be that as a result of the laws of reality, at our scale, we can't use photons to probe infinitely smaller regions of space-time. And expecting photons to be able to do this is kind of ludicrous. The value for the Planck length isn't even all that special. It comes from combining the constants of the universe to get a value for distance. But the values for those constants come from the measurements we are able to make at our scale with the tools we have available, which would mean that the values for these constants may very well be anchored to the limits of our ability to observe the universe at our scale and do not encompass the totality of reality. It's like with our observer from the thought experiment in the first video trying to measure the speed of causality in their larger scale universe. They would be carrying out this measurement using the particles and field that are scaled to their size in their universe. So the values that they would achieve would be physically different than what we measure, even if the observer gets the same answer, because the values for their answer are scaled to their universe. Which means that if the observer tried measuring the other constants of physics in their larger scale universe, the values they would get would be scaled with them. And if they try to combine the values for the constants they measure, they could work out the Planck units, which would also give them a Planck length of their own. This distance would also represent the theoretical limit to the observer's ability to measure the universe. But it would in no way define a limit to the universe itself, just an observational limit based on existing within a particular scale and being made of matter that has real physical properties. To argue otherwise is to make the human perspective the center of everything. To say that all that can exist in the entirety of the universe is that which humans are capable of experiencing. Which is kind of funny in a way, as I'm going to spend most of the rest of this video discussing the cosmological principle, and one reason it holds so much weight amongst scientists is that it's a way to remove humanity from the center of the universe. It's a way to say that we are not special in any way. But the Planck length is an instance where humanity has become the center of everything. Nothing outside of what humans can perceive and experience can even be considered to exist. But the Planck length is not a definitive bottom level to existence. It's just a unit of measurement based around our ability to observe the universe. The claim that it is a hard limit to the universe, a floor to existence, is nothing more than assumption and inference. The Planck length could just as easily be interpreted as nothing more than an outcome of our ability to measure the universe at our scale with the tools we have available based on the properties of the universe. The interpretation I'm arguing for isn't just that there's an infinite scale to the universe, but that structures can exist and continue to form at infinitely larger and smaller scales. This is called a fractal universe. It isn't a new idea or even unknown in science, it's just considered a very fringe idea not worth pursuing. While some scientists are open to the idea that the scale of the universe is infinite, very few scientists support a fractal universe, let alone publish any research on the subject. The consensus view is largely that the idea has already been proven wrong. However, I will try to argue that the evidence currently available could be used to support a universe that is fractal in shape. So what are fractals? Very broadly, fractals are a way to describe the roughness of an object or system of things. For something to be a fractal, it must have a non-integer dimension that persists over a number of scalar intervals. Having a non-integer dimension just describes how rough the structure of something is. A triangle and a cube have smooth surfaces, and so these objects are just 2 dimensions and 3 dimensions, respectively. The more roughness that something has, the higher their fractal dimension will be. For example, the surface of the ocean can be mostly smooth in calm weather far away from land. It contains only a little roughness, such that it could be described as being close to, but not exactly, 2-dimensional. This value would be its fractal dimension. Or the ocean could be extremely rough and uneven during an intense storm, where its fractal value would be closer to, but not quite, 3-dimensional. Fractals are a mathematical concept, so there's a lot more to it than that, but this is the bare minimum required to understand the topic. If you want to know more, then I highly recommend this video by 3 Blue, 1 Brown, which gives a very good overview on the subject. It's a much better and more thorough explanation than what I provide here. While fractals can be very intricate and complex, they are surprisingly easy to make. Take the Mandelbrot set, which comes from a function where the solution to an equation gets entered back into the equation itself, creating another solution that then gets entered back into the equation. From that comes an infinite amount of complexity. The Mandelbrot set is what's responsible for the most well-known images of fractals. Or there's Sierpinski's triangle, which can be made by building a triangle with 3 of the previous iterations of triangles. Or if you prefer to go down in scale, then by repeatedly removing triangle sections from each triangle and every newly created triangle. Really, any pattern can be made into a fractal by making it self-repeating, like this one involving circles. However, examples like this give the false impression that fractals are always self-repeating on infinite scales, which simply isn't true. Fractals are seen everywhere in the natural world, and these are very rarely self-similar and never on infinite scales. Like there is fractal structure in the borders of coastlines, the shape of mountains, the structure of galaxies, and the structure and development of biological organisms. These natural fractals are not infinitely self-repeating because at some point they stop. Fractals made from pure mathematics are not exactly like fractals that are found in nature. This distinction is important because a common criticism to a fractal universe is that the universe itself isn't self-repeating, therefore it can't be a fractal. But this is a complete misunderstanding of what fractals are and what the hypothesis is trying to suggest. The argument for a fractal universe isn't necessarily that it is self-similar and self-repeating at all scales, only that structures continue to exist and form at infinite scales, and that these structures form into fractal patterns over some interval. These patterns emerge from the movement and interactions that occur between objects over time. Because instead of being self-repeating, natural fractals are defined by having a repeating fractal dimension over a decent number of scales. The classic example is the border of the British Island, but really any coastline would work. This coastline has a fractal dimension, or a certain degree of roughness, that stays consistent whether looking at the outline of the whole landmass, or if you zoom in and only look at a small section of the coast. Which should make sense. The landmass was created at the same time, in the same place, under the same physical processes, and so its roughness is, approximately, the same everywhere. Which is also true of all coastlines. They have a fractal dimension that repeats over a number of scales. But the fractal dimension between different islands and coastlines can all vary from one another because they were all created at different locations under different physical conditions. This means they can all have different degrees of roughness, which is how natural fractals are made, from iterative, interacting processes that happen over time in or to a structure. Separate members of the same type of structure can have radically different fractal dimensions because the conditions that created them varied at that location. Coastlines will have a different fractal dimensions from each other due to how they were affected by such things as plate tectonics and erosion. And for the exact same reason, mountain ranges will have different fractal dimensions from each other. The same is true of different cloud formations. Even galaxies will have varying fractal dimensions from each other based on the iterative processes that created and shaped their development. Fractal structure in natural objects, then, comes from the interacting iterative processes that created and shaped those structures over time. Said another way, the roughness of an object is created from the processes and interactions it experienced throughout its lifetime. And these natural fractal patterns stop at some point. The British Island has a definitive size. There's only so far you can scale up before you are looking at the entire planet. And at some point of scaling down, you stop looking at lengths of the coast and start looking at local formations of sand and rock. And going even smaller in scale means you'll eventually be looking at atoms and molecules. But over a reasonable number of scales, the fractal dimension of the landmass is the same. Above and below that are other structures with their own possible fractal dimensions. A fractal universe, then, is one in which the entirety of the cosmos is filled with roughness in infinite directions and possibly over infinite scales. And this roughness develops due to the interactions of everything that exists over time. This roughness would be the arrangement of matter and energy we see in the universe, and the degree of roughness would change at different scales and between objects at the same scale. In a fractal universe, the infinite number of structures present at any scale could cumulatively add up to some larger structure above that. And every structure at every scale would be made up of the accumulation of all the smaller objects they consist of. It's this iterative interacting process that gives the universe its shape and properties. What this would mean is that if you could infinitely change your scale, basically change your size, then no matter how large or small you became, there could always be more stuff in the universe. Below the Planck scale, and above the observable universe, more things could potentially exist in the universe. There isn't a consensus opinion about the shape of the universe, so there's a wide range of beliefs among scientists. The most popular ideas can generally be separated into two major categories. Either that the universe is strictly finite, or that the universe is infinite in size, but not scale. For a number of reasons, largely due to the Planck length being seen as the floor of existence, most scientists believe that there is some kind of limit to structure formation in the universe. That at some point larger in scale than our universe is just a vast, unending nothingness. But there are some scientists that have a problem with infinities existing at all. They view the concept as an invention created in math without direct physical application in reality. They think the universe itself is entirely finite, that the universe we live in is all that can exist, and that there are real physical boundaries to scale after which nothing can exist. That may sound like it shouldn't work with a universe that appears to be flat and infinite in shape. However, there are a number of finite shapes that would be consistent with observation. For example, the universe could be torus-shaped. In very rough terms, this is where the universe looks like a donut. This would technically work because two lines that start traveling parallel to each other inside of a torus will continue to travel parallel to each other forever. But that does mean that this hypothesis is proposing that the universe has some clearly defined geometric shape, which needs some explanation for why and how that came to be. And this is where problems start to arise. Like the question of, what's beyond our universe? If there are clearly defined boundaries to space, then we can at least ask about what would be beyond those edges. And the answer must be nothing. And not like the vast nothingness of space, but an absolute nothing with absolutely no properties at all. If anything did exist beyond our universe, or even if this nothingness has any properties, then it would imply an infinite spatial dimension. Because this substance or these properties could extend outward indefinitely beyond our universe, and the theory would then fall apart. Or there's the question of where did the universe come from? If our universe is all that exists, then what came before it to cause its creation? And the answer must be just the finite universe which created itself, as it's all that exists. And so under this model, it's usually just assumed our universe has always existed, but goes through moments of creation, expansion, contraction, and back to creation again, which will continue to happen forever. And already the finite universe theory has an infinite time dimension. It's not that proponents haven't come up with a variety of answers to these and other problems. It's just that to try to maintain a strict finite universe, they've had to invent strange new physics that can't be tested, is contradicted by other evidence, and only exists to support this model. Which is why a strict finite universe is a position held by a minority of physicists. Although this minority appears to outnumber the proponents of a fractal universe. The more popular view is that the universe is infinite in size in three-dimensional space, but does not have an infinite scale. That the nature of reality limits how big or small things can get. At the smallest scales, this is because of the Planck length, which many physicists assume is the bottom level of the universe. But it's also commonly assumed that there is a limit to how large things can be as well. So if you could somehow scale upwards or grow larger, then you would eventually reach a point where structure formation stops from our universe. Above this point in scale means that all the matter and energy that does exist will get smaller in size relative to your perspective. And at some point it'll all be so small as to be indistinguishable from nothing. And beyond this point in scale, there would only be nothingness, and an infinite void of nothing at all scales above that. One reason for this is of course the belief that the Planck length is the bottom floor to reality. Because if there's a bottom level to the universe, then there's a finite amount of stuff that can exist within any one region of space. So there's a finite amount of stuff to build larger scale structures with. The other reason is that our universe had a beginning, a definitive start date with the Big Bang. This means that there's a finite amount of time for matter to have interacted to form larger scale structures. This is certainly true, which means that it's entirely possible that at some point, structure formations from matter in our universe stops, if for no other reason than the lack of time. But this doesn't mean that matter and energy can't exist at larger scales. It's a possibility with this interpretation, and I will discuss it more in the next video. For right now, an infinite universe with a finite scale is more reasonable than a strictly finite one, but it still leads to some problems. Like, why does matter exist in these scales, but nowhere else in the universe? How is it possible for our universe to form in this small section of existence, but it's impossible for it to happen anywhere else? And there's the matter of why, if matter exists everywhere in infinite directions, doesn't it cumulatively add up to something else at larger and larger scales? Even if structures stop forming in our universe, why doesn't the infinite amount of matter and energy that can exist in all directions out to infinity add up to something else? The most common answer is the Cosmological Principle, which states that the universe is homogeneous at the largest scales. This homogeneity means that the distribution of matter and energy is ultimately smooth, making it impossible for structures, and hence fractals, to form after a certain point in scale. And there's supposedly evidence for this fact, which is a big reason why an infinite scalar dimension and a fractal universe have become fringe positions in physics. The cosmological principle is an extension of the Copernican principle, which states that we are not the center of the solar system. The cosmological principle states that we are not special in the entirety of the universe. More directly, the principle states that the universe is statistically isotropic and homogeneous at the largest scales. Isotropy means that there is no special directionality to the universe. All measurements will be identical no matter which direction an observation is taken. And homogeneity means that the distribution of matter in the universe is uniform, such that the same information will be available no matter where an observation is taken. These two concepts may sound the same, but they are in fact different. Imagine that a piece of lined paper represents a two-dimensional universe where a two-dimensional observer exists in the middle of the page. The lined paper is homogeneous, in that the lines on the page are evenly and regularly distributed throughout. However, the observer will receive different information depending on whether they look left and right, where they would be looking along the directions of some lines, or if they look up and down, where they'd be looking through multiple sections of lines. There is a unique directionality to this universe. The universe is not isotropic, which means that this cartoon universe is homogeneous but anisotropic, which is entirely possible. However, the reverse is not. If the universe is inhomogeneous, it cannot by definition be isotropic, because observations in different directions would necessarily contain a different distribution of stuff, creating unique directionality. Anyway, the consequence of a statistically homogeneous and isotropic universe is that there are no unique positions in the cosmos. All observers will see relatively the same thing when they take measurements no matter where they are in the universe or where they look. No location is special. The implication of this is that the universe stops forming structures at some point and becomes smooth forever after, as it shouldn't be possible to build new structures from a smooth and even distribution of stuff. It is claimed that the homogeneity of the universe has already been verified through numerous repeated experiments, and many principles of physics, including Einstein's equations of general relativity, rely upon it being true. Which sounds like a pretty definitive case. There's theory and experimental data that shows that the universe is homogeneous and isotropic. So let's talk about why that's not necessarily true. The cosmic microwave background radiation is commonly used as evidence for the homogeneity of the universe. This is the radiation emitted some 380,000 years after the beginning of the universe, when the temperature dropped enough for electrons and protons to combine to form neutral atoms. This process emits photons, which physicists are able to detect and analyze. While this map looks like it contains a lot of variation, it's actually a bit misleading. The actual difference from the hottest location and the coldest is only a tiny fraction of a degree, barely anything at all. In order to see these differences, the raw data had to be processed, and what differences do exist are then greatly exaggerated. Without all this processing, the CMB data would look very homogeneous. So physicists generally say that the early universe was homogeneous, which is pretty much true, except that I don't think that the homogeneity of the CMB should be taken as definitive proof that the universe is always and will always be homogeneous, because an even cooling of temperature should be expected. To start, the observable universe and the CMB data are not the entirety of the universe. We know that more exists beyond our ability to measure. How much more isn't yet known, and in fact may never be fully knowable. It's possible to estimate how much more matter would need to exist to explain some of the properties of the observable universe. This wouldn't tell us how big the whole universe is, just a minimum value for how much more must exist near our part of the universe. And the lower end of this prediction has it that the universe is at least 200 to 300 times larger than what we can observe. Of course, the upper limit to this estimate is that the universe is infinite in size. What this means is that the CMB data doesn't show the entire universe cooling at the same rate. If the estimates for the current era holds for the CMB data, then at most, less than 0.5% of the entire universe cooled at very nearly the same rate after the Big Bang. Which is less impressive than how this data is usually presented, where the entire universe cooled at the same time. What's actually interesting is how this near homogeneity turned into the structures that we see today. Because no matter how homogeneous it is, it still turned into variations that led to the formations of structures we see around us. Even most simulations of the early universe include random variations in the Big Bang to account for these inhomogeneities we see in the present day. So the entire universe didn't cool at the same rate, just the small part of it we can see. And even what homogeneity existed in the past does not mean that the present or future are locked into homogeneity. So no matter how homogeneous the cosmic microwave background data was, it does not tell us how smooth the universe currently is. There is, however, research that apparently proves that the universe is statistically homogeneous in the present day. This is primarily done by analyzing the distribution of cosmic objects, usually galaxies or quasars, using three-dimensional maps of space. Starting around one galaxy, a three-dimensional shell of some radius is measured, and every other galaxy in that volume is counted. Afterwards, the radius of that shell is increased, and all the galaxies in that new volume are counted. The radius is then increased again, and all galaxies in this new volume are counted. This is repeated out to some final volume. The resulting data shows the relationship of the number of galaxies to distance away from that one starting galaxy. This process is then repeated for every single galaxy in the map being used, counting the number of galaxies around them at increasingly larger volumes. The final result is a large dataset where the interrelatedness of the distribution of galaxies to one another can be analyzed. From this, the fractal dimension can be found, and if and when there is a turn to homogeneity. There are some variations in how best to collect and analyze the data, but this is basically the process for how the homogeneity of the universe is studied. What will be created from this data is a graph like this. If the distribution of galaxies are correlated, if there is a fractal structure, then the data will make a sloped line. If, however, there is no correlation in the distribution of galaxies, or if the correlation breaks down at some distance, then the data will make a flat line. There are some flaws and limitations to this approach, however. One of the few researchers I could find who talked about this was the late Dr. Paul Coleman, a rare proponent of fractal cosmology. In this talk I'm showing, Dr. Coleman discusses how there are problems with the way the data is analyzed and interpreted by researchers. According to Dr. Coleman, most of the early studies built homogeneity into the mathematical models such that all data analyzed, no matter how it's actually structured, would come out as smooth. Even if you put known fractal data in, these models would still say that it's homogeneous, which means that most of the early work in this field is entirely useless. However, every study done over the last few decades now uses better and more reliable math. But researchers can still bias their work towards homogeneity in other ways. As Dr. Coleman explained, these maps of the cosmos are often incomplete, in that there are areas missing or blocked out. This can be caused by a number of things, like the fact that many of the dish arrays that collect this data are based on Earth, which means that at most they can only map the sky not blocked by the ground. This is important because when the volume around a galaxy reaches one of these gaps in the data, it's best practice to stop analyzing that galaxy and move on to another one, as it is no longer possible to get reliable data. The way many researchers handle this is by filling in these blank regions by copying and pasting data from other parts of the map, or just by creating their own randomized data to fill it in, meaning the results they are getting are based on comparing real data mixed with made-up data. An often cited article in favor of a homogeneous universe is the Wiggle-Z study. The researchers of this paper manufactured data about galaxy location to increase the usable map from about 100 megaparsecs to 400 megaparsecs. They even acknowledged Dr. Coleman in his criticism of this practice, but the response was that they really wanted to use all of the map, not just the parts they actually had complete data for. The researchers claim to have considered any bias this might have introduced, because they also try to see what would happen if they used randomly generated fractal data, which is that it comes back as fractal in nature over the entire 400 megaparsec map, which means that the fake data that they used in the final study was homogeneous. So the homogeneity that this paper claims to have found doesn't come from measuring reality, but from analyzing pre-made homogeneous fake data. And this is seen as acceptable in this field of study. But there's a much more important problem that Dr. Coleman identified. These studies only work when a robust amount of data are available, because otherwise, regardless of the actual structure of the universe, the data will trend towards homogeneity at the edges of whatever region is being studied. Dr. Coleman gave an example of how he did an analysis out to 40 megaparsecs, and the results started to look homogeneous at the edges of that area. But when he repeated the study on that same region, but this time out to 80 megaparsecs, the results showed that the fractal structure extended out to almost the entire 80 megaparsec area. Two different studies on the same region of space done in the same manner by the same researcher gave two different answers. This shouldn't happen. According to Dr. Coleman, this occurred because the Virgo cluster was only partially measured in the first study, which overwhelmed the results and skewed it towards homogeneity. But what Dr. Coleman actually demonstrated here is that these kinds of tests are designed to go to homogeneity at the end of every study, even if the overall structure is a fractal. because what is really happening is that the number of galaxies that can be studied will always decline in number at the edges of every frame being studied. This is shown very clearly by this recent article. They do their best to remove bias and to be as rigorous as possible, even mentioning Dr. Coleman and his colleagues' criticisms, which they do their best to take into account. And their conclusion is that the universe becomes homogeneous after around 140 megaparsecs. However, the researchers also did two other analyses within the same region of space, where only a small section of the total map was used. This is much like what Dr. Coleman did in that previous example of studying the same region of space out to two different distances. But this paper went further and kept track of how many galaxies were still being analyzed at each maximum radii. And from this, it can easily be seen that in each group, the results skewed away from being a fractal once the number of galaxies being studied began to drop off. Which is precisely where the final skewing towards homogeneity comes from. A drop in the number of galaxies being studied. A valid interpretation of these results is that the homogeneity did not come from finding a smooth part of space, but from the data from their frame of consideration running out. If you don't understand what is happening, these studies are done by looking at the areas around a galaxy. Once the radius around a galaxy hits a blank area on the map, it is no longer considered. So when comparing the smallest radii around galaxies, all or almost all of the galaxies in the frame are considered. But as the radius increases, more and more of the galaxies are no longer being considered because they hit a gap in the data, i.e., the edges of the frame. The first of those dropped will be the nearest the edges. This will be followed by those next closest to the edge, and so on. By the end, at the most extreme radii being used, only those galaxies with the most mapped areas around them are considered. These will necessarily be the most central on the map, which will also most likely be the closest to each other. So fewer galaxies are counted, and the area being looked at for each galaxy begins to overlap more and more, to the point where they are all looking at almost the exact same regions of space. So it isn't that the universe gets homogeneous at that scale, it's that the area being analyzed around these galaxies is physically the same region of space, with the same data being analyzed against itself. So these tests are designed to go to homogeneity at the end of whatever frame is being used, regardless of the actual shape of the cosmos. If we had an accurate map of the entire observable universe, and even if we knew for a fact that the entire universe was a fractal, then these tests would still say that the universe trends towards homogeneity at the edges of the observable universe. This is because the galaxies with the largest radius able to be studied would be those that are closest to the Milky Way, where the area of comparison between them would basically be the entire observable universe itself. Which means any comparison between the space around the galaxies would look the same. It's the design of the studies itself that is creating the bias towards homogeneity. The researchers of this paper understood and acknowledge all of this as a possible area of bias, because this is actually well known in this field of study. However, these researchers still conclude that 140 megaparsecs is the maximum distance of fractal structure, because this graph begins to go horizontal at the end of the dataset. But the better, more scientifically consistent conclusion would be that they've only found that the fractal nature of the universe goes out to at least 140 megaparsecs. They did not actually find any homogeneity in their study, it's just assumed to be there when they run out of data. Which is standard practice in the field. Measure, find fractals, declare homogeneity. Because as Dr. Coleman explained, almost all researchers go into these studies assuming the universe is homogeneous, which biases the interpretation of the results. Going back to the Wiggle-Z study, to prove that they were unbiased in their procedure, the researchers show what the data looked like when they only used the regions of space they had data for. And it's exactly the same pattern we see everywhere else. Once the data of that region of space runs out, once it's only the most central and closest galaxies, there's a turn to homogeneity. This is why later studies with larger maps have pushed the known fractal distance out to 150 megaparsecs, while this earlier study with a smaller map has the fractal distance going to less than 100 megaparsecs. Which is why these studies have yet to prove that the universe is homogeneous, because there hasn't been a single study where the homogeneity in the universe didn't come from either manipulating the data or taking a known flaw in the design of these studies as fact. Because the only thing these studies keep finding are fractals with a brief switch to homogeneity at the end of the usable map. And if we look at the historical trends, the fractal distance of the universe keeps scaling up with the size of the maps being used. This is also true when this kind of research is done with quasars. Except that, as a result of how bright they are, it's possible to get accurate data on their position at much greater distances than for galaxies. However, the farther away an object is from us, the further back in time it is. And the environment for the creation and distribution of quasars differs between different time periods of our universe. So these maps are split into smaller sections, to not only separate quasars by approximately similar time frames, but also to make each region of space under consideration more equal in dimensions. This results in 2 or 3 sections that are nearly the same size. And from here, everything about these studies is the same as for galaxies, including how there's always a turn to homogeneity at the edges of each frame because of the flaw inherent in the design of this research. It's also possible to measure the fractal dimension of the cosmic microwave background. While the overall temperature is pretty homogeneous, the differences that do exist are structured in a fractal pattern. Which should make sense, as these differences line up fairly well with structure formation on our universe, which is also fractal in nature. This isn't usually taken as evidence for a fractal universe, however, because this roughness doesn't encompass the entire CMB data. But once again, this isn't how natural fractals work, which can only maintain some kind of roughness over a small range of scales. Beyond this point, large-scale structures can emerge from these smaller-scale fractal objects. And these larger structures can have a fractal dimension of their own, which gives rise to something else, and so on. And all of this could be taken as indications that the universe is, as far as we can observe and measure it, fractal in structure. There is other evidence on the nature and shape of the universe. However, it too could be seen as pointing towards a fractal universe. First off, fractals are seen everywhere in nature. Fractals are seen as small in scale as chemical interactions, and as large in scale as up to 150 megaparsecs across, or just under 500 million light-years in distance. Within these scales we know that the universe can, and generally does, organize into fractal structures. And it's not that it's been proven that fractals don't form above and below these scales, it's simply that there isn't enough data to know for sure. Below chemical interactions we get individual atoms and particles, whose position is best described in probabilities. And I just got done explaining how at the cosmological scale, our knowledge has been limited by the accuracy and quality of our maps. The best scientific description, then, is that wherever we have sufficient and accurate data on position, we are able to see fractal organization in nature. Which should make sense, because fractals are simply when structures are shaped or formed from iterative interacting processes over time. Since all matter in our universe has a common origin, has properties, and those properties interact with the space and matter around it, then we should expect fractal organization over time. So let's talk about what these cosmological studies have actually found. Many recent papers have the fractal nature of the cosmos going out to at least 150 megaparsecs, not accounting for redshift. At that size, we're just talking about superclusters of galaxies. The Laniakea supercluster, for example, of which the Milky Way galaxy is a part, measures approximately 160 megaparsecs across. It apparently has fractal structure. And why shouldn't it? After all, a fractal is a structure where the roughness develops from the interactions between its constituent parts and its environment over time. Galaxies have their own fractal dimension that varies from one another depending on their components and the history of interactions they share. A supercluster is created from a number of galaxies and galaxy clusters forming and interacting with one another. So when the base unit being looked at is a galaxy, of course superclusters are going to come back as fractal in nature. Which is more or less what the studies show, that superclusters of galaxies are, or at least can be, fractal in structure. But superclusters can become much larger than this, up to about 280 megaparsecs, which is just about 1% the diameter of the observable universe. So it shouldn't be a stretch to say that based on current evidence, the fractal nature of the universe might go up to at least 1 billion light-years across. I mean, that has to be the case, right? If it's not, if we can't extrapolate to other parts of the universe, then we must exist in a unique part of space with unique information that is creating a unique perspective from which we see the universe, which would mean that the universe is not homogeneous. Or we can say that other galaxy clusters were created, interacted, and form much like those nearest to us. Although, even if true, this sits well inside what the cosmological principle would predict for the maximum size for structure formation in the universe, which is approximately 1.2 billion light-years across. However, there are numerous voids and structures that are much larger than this limit. The largest is the Hercules Corona Borealis Great Wall, approximately 10 billion light-years along its largest axis, or 10% the diameter of the observable universe. So even what predictions could be made about the maximum size of structures from the cosmological principle are provably false. But let's talk about what exactly a homogeneous universe would actually mean, which is that there is a steady state in the universe where things either stop interacting with other objects, or if they do, then it happens with approximately equal force in all directions at all times, where all forces in the universe balance out and all matter is more or less evenly distributed. This is because if there are uneven interactions, or an uneven distribution of stuff, or God forbid fractal structures at these larger scales, then it means structure formation could potentially still take place from interactions over time. Again, a fractal isn't a thing unto itself. It is a way for a system of things to organize. That organization comes from the interactions and interrelatedness of its constituent parts and environment. For a homogeneous universe to be true, then, structures must stop interacting and influencing other structures, or all forces in the universe are evenly distributed and balanced out. But that isn't what is seen in the cosmos within even just the observable universe. Our location in the Laniakea supercluster makes up an underdense region of space that is being drawn towards some location called the Great Attractor, a region of space near the overly dense, shapely supercluster. So even at the supposed end of structure formation, we still see interactions and forces directing and acting upon nearby superstructures. There's also evidence for superclusters interacting with other superclusters through gravitational filaments, which means we can see the potential for the formation of a superstructure above this scale. Even when simulations of the universe are made, they end up creating fractal structures. However, outside of the boundaries of these simulations, researchers will generally say that everything else is homogeneous and repetitive. What this would mean is that for every feature that we see in the observable universe, there must be a statistically equal copy distributed everywhere in space at regular intervals out into infinity. This includes not just the distribution of mass, but also every dense or underdense region, the momentum and direction of the flow of that mass, the interactions between that mass, and more would have to be more or less replicated infinitely many times in regular intervals of space out into infinity. It should be noted that the cosmological principle was created at a time when nothing outside of the Milky Way galaxy had been observed, when the very idea of galaxies was not yet known. And it was several decades before the idea of fractals had been discovered. So the concept of what the universe actually looked like was dramatically reduced and simplified from what we know today. Which goes to why it found success where it did, such as with Einstein's equations of general relativity. The cosmological principle oversimplifies the universe. It takes all its complexity and turns it into a smooth, evenly distributed sphere, which helps to simplify the math. To summarize, the predictions the cosmological principle can make are wrong. We have yet to measure any homogeneity in the universe, and we do not see a steady state of cosmological forces. What we see are larger and larger structures interacting and influencing each other over time to make other structures. There is no evidence that the universe is homogeneous outside of assumption and manipulation. It does, however, look very much like the universe is fractal in nature. Since all we can see and measure are the formation of fractal structure, then I believe it makes more sense, scientifically speaking, to just continue to assume that fractal structure will continue beyond what we currently can observe and measure. So it may very well be possible to not only have infinitely many larger scales, but for these larger scales to be filled with matter and energy. Because interactions between energy and matter don't need to stop. They could potentially always build into larger scale structures. While few researchers question the homogeneity of the universe, there is a growing body of evidence that the universe may be anisotropic. Several research groups have independently come to the same conclusion. I'll not be spending a lot of time on this, since if the universe is not homogeneous, it can't be isotropic. Since I have come at this debate by questioning the homogeneity of the universe, I don't think it's necessary to cover this in depth. I'll just mention that there's research that has been done on the topic and leave it at that. And that's my general argument for a universe with an infinite scale. For one, there's at least some evidence that the universe might be infinitely large, which would necessarily mean that the universe has infinitely many larger scales. And the argument for a smallest possible scale could very well be based on making the limits of human observation the hard physical limits to the universe. It's at least as likely that the Planck length is just the limit to what we could ever know. And I tried to show that the universe very likely has a fractal structure. This is because natural fractals come from the iterative interactions that a structure has had in its creation and throughout its existence. So over time, we should expect fractal formation with anything that has properties and interacts with other things that have properties. This video can prove that the universe is infinite in scale and fractal in structure. We are all stuck in an observational bubble, and the universe may forever be beyond our understanding. However, I hope that this at least made a decent case that it's possible that the universe has an infinite scale, because this is a core aspect of the interpretation of this series. Having now just spent the last two parts of this series defending the plausibility of this idea, I will discuss the interpretation itself in the following video. So I hope you will join me as I will explore how a model of the universe that is local and real and has an infinite scale could possibly work.